The most popular way to represent signed values is using 2's complement representation. This is used in every smartphone, this is used in laptops, servers in the cloud, this is used throughout computer systems. The reason that it's so popular is it simplifies the design of the electronic circuits, including the addition of positive and negative numbers. Now, the nice thing about 2's complement is the procedure for addition is the same, regardless of the signs of the numbers, whether they're both positive, both negative, a positive and a negative. You do the exact same procedure in the computer. Here are 2 examples where we have the value 5. Now, you should be familiar with this as an unsigned number. This is the unsigned representation of 5. It's the same in 2's complement, and signed representation has the same value. And here's the 2's complement representation of -5, and you'll learn why this is the case in a second. Now, if we add these together using the same procedure of adding each position and the carries moving from right to left, we're going to end up with 0, which is the right number. We add 5 to -5, we should get 0. Now we're going to get a carry out of the most significant position, but we can just throw this away and represent this as a 5-bit value, which is 0. Here's another example where I have 9, the positive value 9, and I'm adding to that -9. And this is the 2's complement representation of -9. Now when I add those together, I again get 0. I get the same result as I got on the left-hand side. I get the positive number adding the equivalent negative number, and I get 0, which is what I should get. Let's talk about how we represent 2's complement numbers. If the number is positive or 0, it's exactly the same as unsigned binary. It's exactly the same that we just learned. To form the negative representation of a positive number is first we start with the positive number. We invert every bit, so every 0 becomes a 1 and every 1 becomes a 0. And then finally we add 1 to that number. So let's take this number 5, 0, 0, 1, 0, 1. The first thing we do is we invert all the bits. All the 1s become 0s and the 0s become 1s. Then finally we add a 1, so we add in the rightmost position a 1, and we get 1, 1, 0, 1, 1. This is 2's complement for -5. Here's our number 9, our number positive 9. Again, we invert all the bits, we add 1, and we get 1, 0, 1, 1, 1. And that's -9 in 2's complement. Here's a handy shortcut for converting from a positive to a negative number or negative to positive in 2's complement. If we copy bits from right to left up to and including the first 1, and then we invert the remaining bits. You'll find sometimes when I do this procedure of inverting all the bits and then adding 1 is I get this long carry from right to left, so it takes me a while to do that. And here's an example where that happens. I take this value, this 8-bit value, it's actually a 9-bit value, and I invert all the bits. Then when I add 1, you'll find that you have a lot of carrying to do, so it takes you a while to get the equivalent 2's complement value. If we use the shortcut, then we take all of the 0s, those 4 zeros on the right, as well as the first one that we encounter, and we just copy those down. And then we take the remaining bits and we just invert them. All the 0s become 1 and all the 1s become 0, and we get the same value as we have on the left. Let's talk about how we form the decimal equivalent of a 2's complement signed integer. In 2's complement, the MSB, the leftmost bit, has a negative weight, which is different than we had in unsigned values. Remember, with unsigned values, all the weights were positive. With 2's complement, the leftmost bit has a negative weight. It has weight -2 to the n minus 1. All the other weights are positive, just like with unsigned values. Now, the range of an n-bit number, meaning the total number, the total possible range of values that we can represent, goes from -2 to the n minus 1 through to the n minus 1 minus 1. So that means we actually have one more negative number in 2's complement than positive numbers. Here's a table now of all the 2's complement numbers of 4 bits and their decimal equivalent. Now the left-hand side we have all of the positive numbers. Now you notice that the leftmost position, which has weight, a negative weight, has value 0, so that negative weight doesn't come into play. We can just think of this, we can just look at the rightmost 3 bits and do the same procedure that we did for unsigned values to get the equivalent decimal value. Now on the right-hand side, we have a negative, we have a 1 in the leftmost position, so that has negative weight. So we do the same procedure as we did for signed values, except we take into account this negative weight. So the leftmost position here, we have a 1, and that has weight minus 2 to the third, or minus 8. The rest of the values are 0, so this is 2's complement for decimal minus 8. The next value, again, has a 1 in the leftmost position. Every negative number in 2's complement will have a 1 there. Now we have a 1 in the rightmost position, so this is minus 8 plus 1, or minus 7 in decimal. Finally, the last value here is all 1s, so that's minus 8 plus 4 plus 2 plus 1, or minus 1. So no matter how long the value, the binary value, if it's all 1s in 2's complement, that's minus 1.